Before we discuss formal charge, we have to review what are valence electrons and how do you determine valence electrons from the periodic table. You're gonna have a periodic table like this most likely, but I'm gonna move helium over here because you'll see why. So on this periodic table, we can determine the number of valence electrons simply by counting the main group elements, which I just call the tall columns. Those are also called families or groups. So the first family has one valence electron. The second family, which we're going to adopt helium over there, has two valence electrons. And then you have 3, 4, 5, 6, 7, and 8. Of course, on the traditional periodic table, helium is over there with the other noble gases over here. But we're going to move helium over there because helium is so tiny, it can only hold 2 electrons anyway. And right after 1, which is hydrogen, comes 2, which is helium. So just mentally move helium over there as an adopted element. So what does a valence electron look like on a Bohr model? We're going to draw a neutral carbon atom. Carbon is over here. It is the 6th element, which means it has 6 protons. That's the atomic number, 6. So we're going to put 6 protons in the nucleus. 1, 2, 3, 4, 5, 6. Because there are 6 protons, which are positively charged, so I'm going to make a quick note of that. We have 6 positively charged protons. We're also going to need 6 negatively charged electrons in order for this to be neutral. The lowest energy level, the one closest to the nucleus, is going to hold just 2 electrons. And as a little bit of a visual clue, that's kind of why. Then you have the next highest energy level, which is going to be able to hold 8 electrons total. So let's draw the remaining 4 electrons to get our total of 6 electrons for carbon. We have 2 on the lower energy level, and then we're going to have 1, 2, 3, 4 on that second energy level. And you can kind of see carbon is 4 atoms in to that second energy level. So why do valence electrons matter? It's important to be able to determine how to calculate or determine the number of valence electrons from the periodic table just based on what column or what group an element is in, because valence electrons are the highest energy electrons. They determine a lot of the reactivity and chemical properties of an element. This is the traditional equation for the formal charge of an atom in a compound. Valence electrons minus non-bonding electrons minus half of the bonding electrons. I mean, it makes sense if you break it down, but in organic chemistry, my professor said something that changed my life in terms of helping me calculate formal charge incredibly quickly, much more quickly than actually trying to calculate it with this equation. To calculate formal charge, it's just valence minus lines minus dots. So if you know the number of valence electrons that an atom just generally has from the periodic table that we just discussed, and you can subtract away the number of lines, which is equivalent to the number of bonding electrons, well, half of it, and subtract away the number of dots, which is equivalent to the non-bonding electrons, or the lone pair. You basically have the formal charge. Look how easy it is if you just remember valence minus lines minus dots. Let's start with this first one, which is nitrate. So we have N in the middle. Nitrogen is in the 5th tall column, so it's going to have 5 valence electrons all the time. Subtract away the number of lines touching it, which is 1, 2, 3, 4, and you're going to have this number, and then subtract away the number of dots touching it. There are no dots or lone pair on that nitrogen, so you don't subtract away anything. Valence minus lines minus dots, we have a formal charge of 5 minus 4, which is just plus 1. If we calculate the formal charge of the oxygen on top, it's 6 minus, so we have 6 valence electrons for oxygen all the time. There are 2 lines touching it, and there are 4 dots. 6 minus 2 minus 4 gives us a formal charge of 0. And I can put the little plus 1 here if we want to. And then we're going to notice something really important here. When you calculate the formal charge of an atom that has the same structure as another atom in that compound, it's going to have the same formal charge. So let's calculate the formal charge of these oxygens in the lower left and the lower right. Let's just pick one because they're the same looking. So this oxygen here has 6 valence electrons all the time because oxygen is in the 6th tall family or tall group. And then we're going to subtract away, so the number of lines, just 1, and the number of dots, there are 6. So 6 minus 1 minus 6, that's going to give this oxygen a negative 1 formal charge. And this oxygen is also going to have a negative 1 formal charge. The cool part about formal charge is that if you add up all the formal charges in a compound, you get the total charge on the entire compound. So this negative 1 and minus 1 are going to cancel out, which means that this entire compound will have a negative 1 charge. Calculating the formal charge for hydrogen is pretty easy because if you see that it has its one line attached to it, it's going to have a formal charge of 0. You can verify because hydrogen has a valence of 1, there's one line touching it, there are no dots. All of these hydrogens will have a valence, or will have a formal charge of 0. This oxygen here in this hydronium molecule, this oxygen, we're going to do 6 minus, so minus lines, there are 3, minus dots, there are 2, so 6 minus 3 minus 2, this oxygen has a plus 1 formal charge. Now let's calculate the formal charge for the sulfur, the carbon, and the nitrogen in this version of this compound, and then in this version of the compound. So the sulfur is going to be 6 valence minus 1 line minus 6 dots. There's going to be a negative 1 formal charge on that sulfur. Carbon is going to be 4 valence minus 4 lines minus no dots, because there's no dots on that carbon here. And that's going to be a 0 formal charge. And then this nitrogen over here on the left is going to be 5 is the number of valence for nitrogen all the time, minus 3 dots, or 3 lines, minus 2 dots. So 5 minus 3 minus 2 is 0. So there's a 0 formal charge. Overall, this compound will have a negative 1 charge. For this one, we have sulfur again, so we're still going to have our 6 valence, minus the 2 lines, minus the 4 dots. So now this sulfur has a 0 formal charge. This carbon still has a 0 formal charge, but this nitrogen here is going to be 5 minus 2 minus 4. So the negative 1 formal charge is now on the nitrogen. Down here at the bottom, we have a sulfur surrounded by 4 oxygens. So if we calculate the formal charge of the sulfur, we know it's 6 minus 0. So valence minus the 6 lines touching it minus there's no dots on it. And that's going to give us a formal charge of 0 on that sulfur. We only have to calculate the formal charge of 2 of the oxygens, the 2 different looking oxygens. So let's calculate the formal charge on this top oxygen, which looked like the bottom oxygen, so it'll have the same formal charge. The formal charge here is going to be 6 minus, now we have 2 lines, and we have 4 dots. So there's no formal charge on these 2 oxygens, 0 here and 0 here. But if we calculate the formal charge on the other oxygen, so this one or this one, it's going to be valence minus lines minus dots. We get 6 minus 1 minus 6. There's a negative 1 formal charge on both of those. If you add up the formal charges, you're going to get that the entire molecule is going to have a negative 2 charge. And now we have a different molecule. We're going to go ahead and put zeros for the hydrogen. And whenever you see hydrogen and it has a single line touching it, it's just a formal charge of 0. So we have these 4 hydrogens here. We already also calculated the formal charge of oxygens that look like this. This structure of oxygen will always have a 0 formal charge. When it's a double bond and then 2 lone pair, that's a 0 formal charge. We also calculated the structure of this kind of oxygen, where it's an oxygen with 3 lone pair, 1, 2, 3, and a single bond. So it looks the same. It's going to have the same formal charge when it looks like that. So this is a negative 1 formal charge. Carbon, we can calculate the formal charge pretty easily. It's going to be 4 valence minus 4 lines minus 0 dots. So that's a 0 formal charge. We can calculate the formal charge of this fluorine down here. Fluorine is in the 7th tall column, or the 7th tall group, which means it's going to have 7 valence electrons, minus 1 line, minus 6 dots. We're going to have a 0 formal charge on this fluorine. And we have a carbon here that we can calculate the formal charge on. You can verify that it is going to be 0. But this nitrogen, it's going to be interesting because it's not going to be 0. If we calculate the formal charge on this nitrogen, it's going to be 5 minus 4 minus 0. So 5 is the valence, minus the 4 lines touching it, minus the 0 dots on it, and we're going to have a plus 1 formal charge. So we have a nitrogen with a plus 1 formal charge and an oxygen with a minus 1 formal charge. But remember, if you add them all up, you'll get the total charge on the compound. And a plus 1 and a minus 1 are going to cancel out, and this compound is actually going to be neutral, so we don't need those square brackets. That's how formal charge works, the better way.